So apparently, Zoom is
Is
recording the meeting now.
Yeah. Mhm.
So here we have done presence and absence. You said Nora is present, also Mansoor, right? Where is Mansoor? Yes. Okay, guys, the tools that we have at our disposal here to teach you are very much limited. I can only share the lecture notes with you and give you explanations on the lecture note here to you. And you have to concentrate on the screen that I have shared with you. And at the same time, try to hear my voice and understand what I say. If you have a question, you can go ahead and ask. If I don't hear your voice, so that ask your question, you can write your question in chat, okay? And at the end, after the class ends and you read the lecture note and there's a point that is not clear for you, you can do not hesitate to contact me via email or via Telegram and ask me your questions. I can have I can even conduct meetings with you if you have a specific question related to the course. Don't worry about that. And we are supposed to take quizzes and midterm exams also in this format. Okay, it is going to be
Oh,
it is going to be very much difficult for me to do, but it won't be very difficult for you. Just like before, you're going to have your homeworks, right? And on the homework front, we're going to have no specific problem because you can write, guys, let me stop a screen share. Guys, on the homework front, we're going to have no problem at all. Why? Because you can write your homeworks on your papers, on your A4 papers, just like before. You can use an app called Cam Scanner to take pictures of your homework and turn it into a PDF file and send it to me very, very easily. And I can correct your homeworks, grade your homeworks, and we're gonna have no problem at all on that front. Yes? So at the end of this lecture, I'm gonna give you an introduction on how to use Cam Scanner also, okay? Cam Scanner is gonna be the tool that you use to send me your homeworks and quizzes and maybe even exams, okay? So guys, Rabungyan, do you hear me?
yes. But it's kind of laggy. I don't know. It's glitching.
Oh, really?
Your video, yeah.
Oh, really?
Audio is still better.
Oh, okay. So, it is good for us to have a group on Telegram.
Yes.
Yes.
Okay.
Robin, please create a group on Telegram and invite
Okay.
all your friends on it. Maybe when I give
Sure.
you homework, something like that.
Mhm.
When you want to give me back your writings, it is good to have a group on Telegram so that we can easily exchange files. And when you email that to me,
For sure.
it's going to be a little bit difficult because I have to go through my emails, find your homeworks, collect them in a folder, make sure that the homeworks for various classes don't get mixed up. But if you have a Telegram group, that those problems won't happen. I think it would be better. Now, let us start trying to learn. Okay, guys, are you hearing the sorry, are you seeing the note tree?
Yeah. Yes.
Yeah, very
Yeah.
good. In the physical classes that we had, we covered note 1 and 2, and you sent me you gave me the solution to homeworks 1 and 2, right? Your papers are all at the university and I haven't corrected them, but the solutions for homeworks, for problems at the end of note 1 and problems at the end of note 2 are put in your LMS system. So you can go there and find the solution to homeworks 1 and 2, right?
Sorry, teacher, but I think the homework too, I don't give you. We are don't give you.
Oh, really?
Yeah, didn't
Yeah.
give you.
Okay. Thanks for telling me that. Thank you very much for telling me that. We're gonna do something. Okay.
Okay, okay, teacher.
Thank you for telling me that. Now, guys, Robin, quiet.
Okay.
Now, guys, this note 3 that we're going to go through is a very practical and useful subject. We're going to use
Sir,
it.
why don't we revise quickly what we have studied, because I don't think we are remembering.
Oh, that is your job to do. You have the lecture notes. You have to study them you have to re-study them on your own
Yeah,
and
but
get
I
the fine
didn't
points.
keep my notebook from dormitory.
What?
Study.
Huh?
I didn't get my notebook from dormitory. It's
Venus,
stored on.
I have given you PDF lecture notes, right?
Yes, but we have written notes on our notebook.
Oh, I know. But studying the lecture notes that I gave you is going to be enough in order to refresh your memory, right?
Oh.
But the main points that we went through was first, directional derivative, right? Which is a huge subject. And the role of the gradient vector in finding the directional derivative. You remember the theorem that told you that derivative of f in the direction of u is going to be gradient of f dot u, right?
Mm-hmm. Yeah.
And after that, in the second chapter, we went through how to write the equation for a plane tangent to a surface in a space using the gradient vector, and how to write the equation for a normal line for a surface in a space, right?
Mm-hmm.
If you remember. If you don't remember this stuff, you have to go back to lecture notes 1 and 2. And now we're going to continue that discussion, and we're going to see one of the most important applications of that subject. Okay? Now, Here, we wanna estimate change in a specific direction. But before we start, let me ask you a question. You see, you have my video also, right?
Yes.
Except for
Yeah.
the screen that I'm sharing, right?
Yes.
Oh, okay.
Yes. Yes.
So guys, we want to estimate change in a specific direction. What do we mean by that? We have a surface in a space, right? We are at a specific point on the surface in a space, okay? Imagine that we are walking on a mountain and the surface of the mountain is the surface that we are on, okay?
Mhm.
We choose a specific direction, uh, and we want to see how much our elevation changes if we move in this specific direction, for example, 1 unit. Okay? There's a specific direction that is given to us. We want to see how much our elevation changes if we move in this specific direction. Oh, is it clear?
No.
Yeah, it is going to get clear. Look, the directional derivative plays the role of an ordinary derivative when we want to estimate how much the value of a function f changes if we move a small distance ds from a point p0 to another point nearby, right? You remember for a function that was of a single variable like function f, if we were at point p0, right, the change that we would see in f written with df if we moved a small distance like ds would be f prime, or the derivative of f evaluated at p0 times ds, right? For example, if we had a function like f of x equal to x2, and we were at point 1 on that function, if we moved from point 1 to point 1.01, meaning a 1% change in x, then the amount that the function f would have changed would be the derivative of f evaluated at 1 times that 0.01, right? So it would be derivative of x2 would be 2x, at point 1 it would be 2. So for function f of x equal to x2, df is equal to 2 times dx when we are at point 1. Do you agree with that?
Yes.
Thank you very much. So what about a function of more than one variable? What about a function of 2 or more variables? Then you know that df over ds according to our prior knowledge, it is equal to gradient dot u. For a multivariable function, df over ds. So if you move this ds into the other side, df over ds for a multivariable function is equal to gradient dot u, right? So from that, we can say that df is equal to gradient dot u times ds, right? What does this mean? What is going on here? So this means this formula that you have here, it means that if we have ds, meaning a small change in the position using the directional derivative, which is this one, we can find the change that happens in the function f here using this formula, right? And this thing that you have here is the same as the directional derivative, right? So if you find the directional derivative of f at a specific point, you can estimate how much f changes when we move a little bit from that point using this formula. This formula says that the amount that f changes is equal to the directional derivative evaluated at point P0, all of it times the amount of change that we have in the position. Guys, is it clear?
Maybe.
Yes?
Teacher, what's the meaning of DS?
DS, you remember, a very good question.
Mhm.
You remember that when we were proving the formula for directional derivative,
Yes.
we had a df over ds, right?
Yes. DF
What
over
was
DS. Yes.
s over there? The s was when you chose a direction like u, right?
Mm-hmm. Yes.
And you cut the surface at that in that direction,
Mm-hmm.
yes?
Yes.
In the intersection of that plane with the surface that you have in mind, you would have a curve
Yes.
which could be shown in a 2D space, right?
Mm-hmm.
The, the horizontal parameter for that curve would be S, if you remember.
I got it. Thank you. Yes. Yes. Yes.
Now, in this context, you can consider ds as the amount of change that we have in the position of the point that we're at on the surface. So we are at point P0 on the surface. We change a little bit that you can call that little bit ds.
Teacher, can you show us the graph of this?
Yes, yes. But I would have to go to another note. Now, ds is going to get clear when we go through the examples, okay? So wait a little bit for that, and you're going to see what it means. So estimating the change in a direction u. In order to do that, to estimate the change in the value, guys, please pay attention. To estimate the change in the value of a differentiable function f when we move a small distance ds from a point P0 in a particular direction u. If you want to estimate this amount of change, we can use this formula as we explained all the way through here. This formula says what? Says that the change, the amount of change in the multivariable function f is going to be equal to the amount of the directional derivative times the small change that we have in the distance from the point P0, right? Now, we're going to use this little conclusion to solve examples, right? Now, let me ask you a couple of questions before we go through the solution of the example. Manage participants. Oh, Mr. Sarkar is here. Hi, Mr. Sarkar.
I think he left the.
Oh, really?
He left. Yeah.
Yes.
So, guys, let me ask you a question about the directional derivative. So, Rinos.
Okay, teacher.
Rinos, tell me, if we are at a specific point on a surface,
Okay.
what is the direction of no change? So how do we choose the vector u so that we see no change in the value of f?
If the dot product of the I don't remember, teacher.
Oh, very bad.
I will try to revise it.
Oh, you have to.
Yes.
Venus, do you remember?
I don't remember anything, sir. Do not ask me.
Oh my God. Rabul, what about you? I asked him, we are at a specific point on a surface. We want to choose u in a way that we have no change, meaning the directional derivative would be 0. How should we choose u in order to achieve that?
Teacher,
Go ahead.
I think the function of r in the direction perpendicular to the gradient
Aha. The
of
direction of
f.
u, exactly. The direction of u has to be perpendicular to the direction of gradient. Exactly. Exactly. Very good. Now guys, let us go back to the examples. So guys, note 3, example 1, it says, please look at the screen when I'm talking. Estimate how much the value of f of x, y, and z equal to y sine of x plus 2yz will change if the point p, x, y, and z moves 0.1 unit from this point p0, 0, 1, 0 straight toward p1, 2, 2, minus 2, right? Now, according to the formula that we have here, what is it that we need to do? We have to find the directional derivative at point p0 equal to 0, 1, 0, and the value of ds is given to us, right? The value of ds that we need in this formula is given to us in this example, and it says it moves 0.1 unit, right?
Mhm.
So ds is 0.1 unit. So if we find the directional derivative, the problem is solved. We multiply the directional derivative by 0.1 units, and we're gonna estimate the amount of change that we have in f. Yes? Now, we want to calculate the directional derivative. How do we do that? We
Round the f over round the x plus round the f over round the y plus round the f over round the z at t0.
that thing that you said was correct, but it had problems because you forgot the vectors I, j, and k. If we want to find the gradient, as Venus said, if we want to find the gradient, we first have to calculate round f over round x times I plus round f over round y times j plus round f over round z times k. But round f over round x for function f equal to this is what? Y times cosine of x plus 0, right?
Yeah.
So here we have y times cosine of x times I plus round f over round y. Huh? Round f over round y
X.
is, go ahead, sine of x
Sine
plus 2z.
plus 2z.
Okay, so sine x plus 2z, sine x
J.
plus 2z times j. Huh? Times j and round f over round z, which is
2y.
2y times k, right? This is our gradient vector. Yes, this is our gradient vector everywhere. For this specific point, we have to evaluate this gradient vector at point 0, 1, 0, right? When we do that, what's going to happen? 1 times cosine of 0, which is 1i, which we have here. Instead of x, we put 0. Instead of z, we put 0. We're going to have 0 plus sine of 0, which is 0, right? So this term is going to disappear. It's going to get eliminated. Here, instead of y, we put in 1. We're going to have 2k, right? So the gradient of f at point 1, 0, 1, 0 is I plus 2k. Now, the more important problem in this type of examples is to find the vector u. We have found the gradient vector. This part is done. It is equal to I plus 2k. But we don't have the vector u. So we have to first find vector u in order to be able to calculate the directional derivative, right? Now, how do we find the vector u? Please pay close attention. The example says, look at the example. It says we move from point P0 equal to this straight toward point P1 equal to 2 minus 2, right? This is what we are doing. So we're looking for a vector u. What is your suggestion?
Teacher, we can do something.
Go ahead.
P1 minus P0,
Mm-hmm.
we can get a vector, and the unit vector of this vector is equal to u.
Exactly.
Mhm.
So the vector that has the starting point at P0 and finishing point at P1 and has a length equal to 1 is the vector u that we are looking for. So in order to find the vector u, it is enough to calculate the vector P0, P1, which is calculated here, and then divide this vector by its length to get the vector u, right?
Yes.
Is it clear to everybody?
Yes.
Very good.
Yes, teacher.
Alhamdulillah.
Yes.
Very good. So, in order to find the vector p0, p1, we have to have the coordinates of p1 and subtract from that the coordinates of p0. So 2, 2 minus 2 minus 0, 1, 0 is going to give us 2, 1 minus 2. 2, 1 minus 2 is this vector in the component form, right? Now the length of that vector that we have found is a square root of, well, 2 to the 2 plus 1 to the 2 plus minus 2 to the 2, which is equal to a square root of 9, which is 3. So if we divide that vector by 3, we're going to have 2 over 3 I plus 1 over 3 j minus 2 over 3 k. This is our vector u. This is our vector u, and we are ready to calculate the directional derivative. Am I right?
Yes.
So, in order to calculate the directional derivative, we multiply the gradient vector, which we previously calculated at the first step, by the vector u that we found, or the direction vector. The dot product of these two vectors is equal to what? In order to get the dot product, we multiply the components that we have together and add them up. So 1 times 2 over 3, yes, plus for j here, we don't have a component, so the length in the j direction is 0. 0 times 1 over 3 is 0. 2 times minus 2 over 3 is minus 4 over 3, right? So 2 over 3 minus 4 over 3 is equal to minus 2 over 3. This is the value of our directional derivative. Is it clear? Yes?
Yeah.
Yes.
Very good. Very good. So now, the change df in f that results from moving ds equal to 0.1 unit away from point P0 in the direction of u is approximately, using the formula that we talked about, df is equal to this, the value of the directional derivative, times ds, meaning minus 2 over 3 times 0.1, right? Which is going to be equal to minus, approximately minus 0.067 units, right?
Yeah.
So if we change from that if we move from that mentioned P0 to that mentioned P1, to a value equal to 0.1 units, we see that the function f decreases. This negative sign that you see here means that the value of the value of f decreases, but the amount of decrease that we have here is very much smaller than the amount that we have moved. So if you imagine rise over run for the function, we see that f has decreased, but very, very slowly, okay? That is the conclusion that we can draw from this example. We're gonna see another example just like this one, and go ahead and ask me questions if you have. Guys, are you awake?
Yeah.
Yeah.
Everybody who is awake, please.
Yes.
Yes, teacher.
We are awake.
What?
We are awake.
Afari. Alhamdulillah.
Yeah.
Mayad, where are you?
He's watching movies.
I'm sure. Mayad, what movie are you watching right now?
Nothing.
So guys, let me, because this is the first one I'm recording a Zoom meeting, let me stop recording and see whether or not the recording has been done correctly, and then we're going to continue. Okay?
Okay.
Thank you very much.